Before we start, let me make a brief announcement in Korean first. So please bear with me, Salman. 자, 안녕하십니까. 샤논 및 튜링이라는 콜로퀴엄을 이번에 새로 시작하게 됐습니다. 그래서 이번에 첫 번째 연사로 모신 그 USC의 살만 아베스티머 교수님을 모시고 저희가 첫 번째 강연을 시작하려고 합니다. 몇 가지 그 중간중간에 연사께서 뭐 인터랙티브하게 질문을 원하시는 분들은 질문하셔도 좋다고 하니까 질문하시고, 혹시 한글로 채팅창에 질문을 올리셔도 저희가 그 끝나고 Q&A 시간에 번역을 해서 답을 드리도록 하겠습니다. 질문을 하도록 하겠습니다. 그리고 지금 유튜브와 그 다음에 줌으로 동시에 사이멀캐스트 중이고요. 유튜브는 한 테스트를 해보니까 6, 7초 정도 딜레이가 있으니까 감안하셔서 조금 딜레이가 있다는 거 감안하셔서 진행을 해주시면 좋겠습니다. Okay, let me go back to English. Okay, let's start the first talk in this Shannon meets Turing colloquium, and I'll just make it abbreviation as sharing colloquium. So let me make it brief. Professor Salman is on USC Amazon Center, and it makes perfect sense because, you know, Amazon is like basically a distributed network of computers itself. So Professor Avestimehr is actually an expert in distributed computing and distributed machine learning. So it's I guess it's a perfect match between Professor Avestimehr and USC. And he received numerous awards, and he received James Massey Research Award from IEEE Information Theory Society, and many other joint paper awards, and including like David Sacrison Memorial Prize from UC Berkeley, EECS. He has other best paper awards. And he was a general co-chair of ISIT, the prestigious Information Theory Symposium, ISIT, last year. And he's a fellow of IEEE. So without much ado, let's welcome Professor Avestimehr with a big round of applause.
Thanks much. Thanks for the kind introduction. It's a pleasure to be here. First, before I start, maybe I want to encourage everybody, in case you have questions, feel free to ask your questions in the middle. This way we can make it more interactive. It is late at night here, otherwise I may feel sleepy. So as you can see, the title of this talk on trustworthy and scalable federated learning, this is like a new research area that in the past couple of years, my group has been working on, and my goal is to tell you a little bit about this research field. As you can note, this is joint work with quite a few people: Jin-Hyun So, Chayang He, Saraf Prakash, Roshdi El-Kurdi, who are currently PhD students at USC. Basak Guler, she was a postdoc in our group. She is now a professor at UC Riverside. And my colleagues, Professor Murali Anavaram and Mahdi Sultan Al-Kotabi. All right, so a little bit motivation, although, you know, in today's world, the issue of distributed privacy-preserving machine learning doesn't need much motivation. But the whole point here is that, as we all know, we are surrounded by a lot of AI-assisted devices. These are devices that collect a lot of information. They are equipped with machine learning and AI to help us in our daily lives. The challenge is that there is a lot of data that is collected at the edge of these networks. For example, lots of images that you take, a lot of the voice, video that is taken by such devices. And we all know in order to train better and better models, you need to use users' data. But these users' data are very private. They are my images, your videos, your voices, etc. So that's why there is a growing interest on how to do learning distributedly across massive number of devices in a way that we protect privacy and security of the users, and we create trust. Trust in the sense that what is learned across the users is reflective of what they have collected. Okay, so that's the main problem. As you can imagine, this is a very challenging problem. But what has happened is, in the past couple of years, federated learning has emerged as a promising approach towards solving this problem. So federated learning at a high level is very simple. What it says is that keep the data set locally at the users. For example, your images, your voices, your video stays at your own device. Then you train locally at each device. Once you come up with a new model that you have locally trained, then you average it across many users in the network to come up with better model. You push it back and this iteration will proceed. So at a high level, it looks a simple approach, local training, global averaging. But once you start looking into it, this is a very challenging problem, and there are many exciting research problems here. So in our group, we are interested in 3 domains in federated learning. One of them is about foundations of algorithm design. And there are many questions to ask there. Another area is about the scalability and system design for federated learning. The third pillar is trustworthiness aspect of federated learning. In the foundation part, the type of questions that you may ask is model aggregation being the key part of federated learning. The question is when, what, and how would you aggregate across many users? Another issue that distinguishes federated learning from a typical distributed learning is that the distribution of data across different users is very different. That is referred to as data heterogeneity. And also, different users may have different personalized tasks. And furthermore, there should be a notion of fairness. The goal is to collaborate to come up with a fair model for everybody. How to study that in decentralized federated learning. Another aspect of it is that typically, although users have the data, they don't have the labels or annotations of the data. So how would you do unsupervised federated learning? In order to scale these systems, a major constraint is that these devices are often resource constrained, and you cannot fit large DNN models that typically are used in machine learning. So the question is, how would you run federated learning and do local training for state-of-the-art models? Another aspect is, as the number of users increase quickly, imagine, for example, Alexa users or phones, etc. There are orders of hundreds of millions. State-of-the-art studies are limited to thousands. How would you scale from thousands to millions? And also another part is, while models are developed for in a centralized environments, one question is, what are good models that work well on different devices? So how can we have a federated neural architecture search to adapt the model to the user's constraints? Finally, on the trustworthiness pillar, there are many questions like how to do secure and resilient model aggregation, how to tolerate adversarial users in the system, and how to leverage potential hardware capabilities like trusted execution environments in federated learning. So as you can see, there are many research questions here, and we have recently established a new research center in collaboration with Amazon. This is called USC Amazon Center on Secure and Trusted Machine Learning, in order to initiate exciting research projects on these directions. So if you are interested, here is the website of our center. You can follow the news coming from the center. Now, for the rest of the talk, my goal is to tell you a little bit about some of the works that we are doing on the trustworthiness and scalability aspects of federated learning. On the trustworthiness, focusing on secure model aggregation and dealing with adversarial users, and on the scalability, the issue of running federated learning over resource-constrained users. Okay, so that's my plan. Maybe let me pause here. If you have any questions on the overall view of federated learning or activities, please feel free to ask now. Otherwise, we are going to zoom in into some of these research directions. All right, so the first part is model aggregation, which, as I mentioned to you before, is a key component of federated learning. And in particular, we want to understand the privacy and security aspects of model aggregation. So a quick recap in federated learning. If you recall, the idea was you train locally. For example, let's say there are n users. Each of them trains a model over their own data set. For example, at iteration t, user 1 comes up with model x1 of t, user 2 comes up with model x2 of t, and user n comes up with model xn of t. Now, after that, the server, for example, over the cloud, this can be Siri server, Alexa server, Google server, etc., is gonna pull the trained models, average them. For example, a weighted average with a weight pi denoting the importance of user I, to come up with a new model update that is later pushed back to the users for the next iteration. Now, a key component here, although in federated learning, the data stays at the device and the users only update or upload the model updates, there is still possible for privacy leakage. And that's because of something called the model inversion attack. The idea of model inversion attack is that from the trained model of the user, you can invert it and learn the data set at the user. The reason being that these models are typically very large and they memorize the data. There are many attacks like that. Here is an example by the work of Fredrickson et al. What they show here is an image that is reconstructed from a locally trained model. Here is the actual data set that was used for training the model. As you can see, you can do a pretty good reconstruction. So the first component is, although the data has stayed locally, if you don't protect the local models, individual model of the users, still privacy would be leaked. That's why a key component of federated learning is secure aggregation. Secure aggregation would mean we want the server to learn the aggregate of the models. Aggregate is just the average of the models, but not learn the individual models. So the question is, how could the users create a mechanism in which the federated learning server is learning the average of the models, but is not learning the individual models? So there are various threat models. For now, let's start with a simpler threat model, which is all the users on the server are honest but curious. What it would mean is they follow the protocol, but they are curious and they will learn as much as they can. And a fraction of the users together with the server, for example, half of them, may collude with each other. Under this threat model, we want to make sure that still no local model of the users are learned. How can we do that? So this problem was first looked at by a paper by Bonawitz et al. From Google and Cornell University called Practical Secure Aggregation. And they came up with the first approach for secure aggregation. Let me explain to you how they did that. They have several ideas. The first idea was borrowing a simple concept from cryptography called additive mask. And the idea is that each user is going to mask the model with a noise. For example, user 1 masks it with Z1, user 2 masks it with Z2, but user 3 masks it with a noise that would cancel out the aggregate of the noise of the other users, meaning negative Z1, negative Z2. Now, what you can see here is that once these are provided to the server and the server adds them up, then the noises would get canceled out, right? This would mean the server would learn x1 plus x2 plus x3, but it won't learn the individual x1, x2, x3. The reason it won't learn it is because each of them is protected by a noise. Okay, so that was the idea. It is called additive masking because it has this additive structure that if you add the noises, they will cancel out and they will become zero. So now, as you can see in this approach, the server is only learning the aggregate of the models, but not individual models. But unfortunately, the problem is not as simple as you think. And the main reason for it is delayed or dropout users. So as you can see, this design is very fragile. If one of the users, for example, the third one, gets delayed or simply leaves the network, then the server is only learning garbage from the other users and no noise would cancel out. And the issue of dropout or delayed users in federated learning is very critical because this is across millions of devices that all the time may be busy with other things. For example, you may be taking a call, or you may turn off your phone, or you may not have connection, or etc. Okay, so in general, a large fraction of the users may be dropout or delayed. And this design is very fragile. So there are two questions that would arise. How would I create this additive structure? How would I tolerate the delayed users? So let's see how that problem was solved. In order to create the additive structure, the idea has been to do a pairwise key agreement between any two users. For example, any two user U and V would generate a pairwise secret key that they would agree on. They call it the pairwise random seeds. And then these seeds are used for generating this additive mask that I mentioned. How is it done? This part, the noise that is used at user U is going to be the summation of the noises generated from the seeds of the users after that minus the users before it. This way, any noise would appear once in the positive term, once in the negative term, and if you add all of them up, they will cancel out. That's how you are getting the additive mask structure. There is also, a private random seed that is generated at each user to protect its own model, but that one I'll come back to it later. Nevertheless, the first key component is that by doing the pairwise secret agreement, you can create this additive structure that I mentioned to you before, like Z1, Z2, negative Z1, negative Z2. Now let's see how the dropout users are revealed. In order to tolerate these dropout users, these pairwise seeds are also secret shared across all the users in the network. What it would mean is when two users U and V agree on SUV, they secret share it with other users. Secret sharing, is there a question?
Probably not, yeah.
All right. So secret sharing would mean that you share your seed in a way that individually other users won't learn it, but collectively they can help the server to learn it. Now let's see how that helps with the dropout. Once we do that, at the end of each iteration, there is a set of users U that are surviving, another set that is dropout. The server is gonna say to all the remaining users, give me the secret shares of the dropout users. Once those are provided, the server reconstructs their pairwise seeds, manually cancels them out. All other noises here between them would be canceled out automatically because you have the additive structure. Okay, so this would require cancellation of, like manual cancellation of the dropout users by the server, and automatic cancellation because of the additive structure of the surviving users. So as you can see, the scheme has essentially three main components: creating pairwise seeds, using the pairwise seeds for additive masking, and leveraging secret sharing and reconstruction for tolerating dropouts. So how does it perform? Here is the performance of the scheme over experiments over Amazon Cloud. What we have done, we have run the scheme over Amazon EC2 Cloud. We have looked at model size of 100K with 32-bit entries. On the x-axis is the number of users. We have varied it from 1 to 200. And on the y-axis, you have the runtime of the scheme. There are three plots corresponding to how much dropout would you have. This one is for 10% dropout, 30% dropout, and 50% dropout. What you can see here is that, first of all, as more and more users are going to be in the system, the scheme is becoming quadratically more complex. Okay, so this is always increasing quadratically. And another part is that as there is more and more dropout, it takes substantially more time. The reason for both of these two is that it is quadratic, because remember, it required quadratic number of secret shares to be masked to be pairwise, to create a pairwise agreement on and doing the secret share. And the problem becomes more complicated because as there is more dropout, if you recall, the server needs to do more work for manual cancellation. And that's the price that is paid here. In fact, if you look at the breakdown of the scheme, for example, at 200 users, this is the total runtime for 10%, 30%, 50% dropout. As you can see, the bulk of the time is spent at the reconstruction at the server. Okay, so that part is really cumbersome, quadratically getting more complex, and as more and more dropout is taking more and more time.
I have one quick question.
Yeah.
What's the advantage of this pairwise secret sharing over this conventional like single masking?
Very good.
Because I may be missing at the beginning. Yeah.
Yes. So the pairwise is used in order to create the additive structure. Okay, so remember, the goal is how would these three users come up with three noises that if you add them up, you will get 0.
Ah, okay.
So these are like correlated noises.
Mm-hmm.
And for that, one way to do it is through pairwise agreement. So let me explain a little bit here. Let's say there are only 3 users.
So in the end, at the server, you can get a 0 noise because you can make them canceled out. Is that?
Exactly, assuming that all of them respond.
Okay. Okay.
And the way you would do it is by pairwise agreement to create the noises. Like this is how you create the correlation across the noises.
Okay.
Okay, so for example, here, let's say there is only, maybe 3 of them, so that I can simply write the noise here. You have your model X1, so you will add pairwise Z12 plus Z13. Z12, Z13 is like based on the pairwise agreement between 1 and 2 and 1 and 3. So this is user 1, this is user 2, this is user 3, right? Here, your model is X2. Remember the negative term for the one before? So minus Z12 plus Z23. Here, all of the other users are before, so it's going to be negative Z13, negative Z23, right? Now, all these noises, if you add them up, that's what I was trying to say. Each noise appears once. For example, this one in the positive, this one in the negative. This one in the positive, this one in the negative, they cancel out.
Wow, this is a kind of a neat idea.
That's right. So you need that. So you need this pairwise agreement for like correlation between the noises, so you will get 0. The secret sharing part is not about that. It's more of what if this user gets dropouts? Then the way to do it is the seed of Z13 and Z23 should be shared among the other ones, so that they can help the server to recover it.
I see.
Okay, and that's the
shared. That's the idea.
Pardon?
The seed, the random seeds needs to be shared.
Exactly, and that's as you mentioned, that's a usual sharing.
Okay.
The way, so these guys will share it, so the server can reconstruct the seed, this part, and manually cancel it out because it's not automatically getting canceled.
Okay, great.
Very good.
Yeah,
so now the bulk of the time, that's what I was trying to say. The heavy part is really this cancellation, because it requires reconstruction of the seeds at the server, and there is quadratic number of them, and then generating the noise and canceling it. And that's the table that I was showing you in the experiments. This is the bulk of the time spent for the reconstruction at the server. Communication part, all other parts are quite light. Very good. So the first question is this fundamental? In the one hand, it seems because of these, pairwise secret sharing that is needed for creating the additive noises or correlated noises, you will need to pay for this quadratic barrier. But as I'm going to show you, you won't need it. And the first result, I want to talk to you about is Turbo Aggregate. This is a scheme that we have developed. On the same plot, I'm showing the performance of Turbo Aggregate. There are different versions of it. For now, look at the purple one, which is the best Turbo Aggregate. As you can see, its complexity grows linearly, almost linearly in the number of users. And also, you don't see a difference between 10%, 30%, 50% dropout. The way Turbo Aggregate does it is by leveraging coded computing that I'm sure some of you are familiar with. This is a new research area that leverages coding for injecting computation redundancy. And here we need computation redundancy in order to deal with dropout users. Okay, so what I want to tell you, just at a high level, give you ideas on how coded computing works. Because as you can see, not only breaks this quadratic barrier, it also provides significant speed up over the schemes that we were looking at that time. There are three major components of Turbo Aggregate. One of them is leveraging a circular aggregation structure as opposed to a star topology of talking to the server. Still, we will use additive masking for masking the local models. But in order to deal with the dropout, which was really the bottleneck of secure aggregation, we are going to leverage coded computing, in particular Lagrange coding. So let's see how it works. As I mentioned in the first part, we use a circular aggregation. The idea is that we group the users into n divided by log n groups with log n users in each group. Once you partition that, then the aggregation is happening across users in a circular manner. What it would mean is that these users are passing the model to the next. These users are going to look at the aggregate of the previous group, pass it to the next. And as you go to the circle, at the end, the server is going to learn the aggregate of all models. These approaches are typically much more efficient. And in fact, in distributed learning, ring or reduce approaches are often used to speed up aggregation of the models. Okay. Now, the problem with it is, of course, when a user wants to pass the model to the next group, it needs to protect it so that the other users don't learn the local model of the user. And for that part, we use the same additive structure that I explained to you. The cost of it won't be much because you only need to create pairwise agreement between one group to the next. And since the size of each group is log n, for example, you have log n users here, log n, then the total number of pairwise agreements is going to be log n squared. And since there are n divided by log n groups, if you multiply all of them, you get n log n number of agreements. This is much smaller than the quadratic that was needed before. Okay, so that's how we would resolve, relying on less number of pairwise agreements. All right, so once you do it, you will pass it around, means that each user masks it and pass it to the next group. And then each user is also getting the aggregate of the previous group. It also masks it and passes it to the next group. What will happen is once, for example, this user is getting the masked from the mask aggregate from the previous group, all of the user is gonna add them up. And if you add all of them up, something you can show is that this aggregate would be the same as mask aggregate of everybody before you. Okay, so that's what you need to do. But the major issue is, what if one of them gets canceled out? Then in that case, although you were doing additive masking for passing the aggregates, the noises won't cancel out. Previously, that would have required secret sharing of the pairwise across the users, reconstructing at these users, etc., which is very heavy and creates a bottleneck. Instead, as I mentioned, what we want to do is create redundancy in what is passed from the previous group to the next. How do we do that? The idea is, for example, if a user has a model that wants to pass, for example, created the masked model to pass, it also created a coded version of that mask model. The way it would do it, by applying Lagrange coded computing, what it would mean is pass a polynomial through those masks and create some other points on it. Unfortunately, I won't be able to tell you the details of Lagrange coded computing, but if you are interested, you can look at our paper. In the same manner, the user is also going to create the coded version of the masked aggregates and pass it. Now, the key component here is that we need coding, aggregation, and masking to commute with each other so that once the coding is applied to the mask model, that would correspond to the mask version of the coded. And the good thing is that since all of these operations are linear, they are commuting with each other. Now, once you have that, essentially you will get such a picture. Each user is passing the mask aggregate as well as a coded version of it. Now that's okay, because if at this user, one of the users are getting dropped, still there are more coded version that would allow for recovery of what this user should have been told you, like the noise at that user, and doing the cancellation. This method doesn't need any secret sharing and doesn't need the recovery of the secret sharing. It only relies on local decoding at the user. And the local decoding for Lagrange coding is just polynomial interpolation that you can do very efficiently. All right, let me skip the example. With this scheme, what you can guarantee is that, first of all, the aggregation overhead is the n log n that I showed you at the beginning. You can tolerate up to half user dropout, means that as long as half of the users in each group have dropped, still you have enough coding for recovering for the dropout. And also because of the additive masking, the privacy of individual user model is preserved as long as less than half of the users together with the server are colluding with each other. But let's see, how does it perform? As I mentioned to you, there are different versions of Turbo Aggregate. They depend on how would you do the aggregation topology design. Circular aggregation is only one, but you can do better than that. And the best one we have found is hierarchical aggregation. It's like creating a tree topology for the aggregation. Now, the experiment result that I showed you, as I mentioned, we are doing over Amazon EC2 with the parameters of the 1 gigabit per second bandwidth, 100K model size, and user dropout with probability P. And that's how you are getting the results that I mentioned to you earlier. So as you can see, ideas from coded computing can be leveraged to effectively deal with user dropout and reconstruction of delayed users in federated learning. And practically, they provide an impressive gain and make them appealing. And here is the breakdown of the performance for Turbo Aggregate. Something to note here is that these encoding and decoding parts are really very light, and they are much more, take much less time than the manual reconstruction that needs to be done at the server. And that's how you are getting the gains. All right, so let me spend a little bit time, given that this area is growing fast, tell you some of the interesting research directions along the line of secure aggregation. So in order to do that, let me mention some of the drawbacks of Turbo Aggregate. One of them is that this requires passing or communication from one user to the next user. Although it doesn't require direct communication, like all of that communication would go like through internet, still you need to communicate your model to the next. The problem with that one is, in some scenarios that requires more memory size, like for example, doubling the memory at the device and putting more burden on the users. And sometimes you don't want to do that. Another constraint of it is that this communication cost of Turbo Aggregate grows as the model size times log n, because each model, remember, was passed to the next, all of the users in the next group, and there are log n users. So it's going to be as L times log n. And given that the model size is large, sometimes this communication grows rapidly. For both of these, there have been works to address that. One of them is a method that doesn't require communication across the users, but it still gives you these n log n overhead. That's the paper that if you are interested, you can take a look. Another one is the work by Sonan Kade, Kanan Ramchandran et al., that they resolve this n log n communication complexity, and from n log n, they make it like L plus just some additive term. Nevertheless, there are these optimizations, or there are these approaches that you can take on top of Turbo Aggregate. Well, let me tell you some of the open research directions here. The first one is, so far we discussed honest but curious model, but it may be that in the system you have some Byzantine adversaries. What it would mean is that maybe there is one user that is injecting a bad model. Now, the problem is typically, in order to catch the adversary, you need to examine the model that is provided by the adversary. But if we are doing secure aggregation, then the cloud server is not supposed to see the local models. It should only learn the sum of them. So the question is, how would you detect adversarial models without seeing the individual models? So it seems impossible to do. But in a recent work, we have shown actually there is hope for solving that. So first, note that there are two common methods for outlier detection in machine learning. One of them is a performance-based outlier detection. Another one is a distance-based outlier detection. Distance-based would mean trying to figure out which of the models are more different than the other one, according to a distance, and throwing it away. Performance-based would say, let's try the models on, let's say, a public data set and figure out which one of them gives a poor performance, and maybe that's the bad model to drop. In this paper, what we have shown is that for distance-based outlier detection, it is still possible to run such mechanisms while ensuring the privacy of the local models. The way you would do it is you need to make sure this distance calculation can be done in the encrypted domain. Okay, so that would require verifiable secret sharing of the model across the users, secure outlier detection, and then applying secure model aggregation. Let me skip the details of that scheme for the interest of time. But something you can see here, this scheme BRIA, as you can see, if you are adding 30% Byzantine users, still the performance doesn't degrade, while the usual federated learning schemes like federated averaging, as long as you add adversaries, the performance severely degrades. So what it shows is you can have secure aggregation in the Byzantine adversarial setting. But the complexity of this scheme goes back to quadratic. So one open question is, can somebody overcome this quadratic complexity for Byzantine resilient secure federated learning? We don't know the answer to that. Another one is, how about the performance-based outlier detection? Is there a way to have those resilient schemes in the while preserving the privacy of the users? Another direction is, so far I assume that all the users are using the same model, they are quantizing and compressing uniformly, and also we are doing linear aggregation. As you can imagine, in federated learning, there may be a variety of the users, different models at the users, different compression at the users, and the aggregation may be not a simple weighted average. So how to generalize secure aggregation to those settings is not explored and is a wide open area. What we have done for heterogeneous quantization, we have some work that addresses how to do secure aggregation with heterogeneous quantization. All right, so that's for the first part of the talk. Maybe it's one quick question to Sangbuk. How much more time do I have? When do you want me to conclude?
Maybe we have enough time until like 1:30.
Oh, you have a lot of
more time you spend, the better for us. But because
right.
it's late in the evening there, so I guess you can choose your timing.
Very good. So let me go maybe to the other parts a little bit more rapidly, and maybe in the next 10-15 minutes, I can wrap up the talk. Very good. So the first part, I spent a lot of time on the security and privacy aspect of federated learning. I want to spend some time on the scalability and the issue of resource constrained users. What it means is that so far I assume that each user can locally train a model. But these models are big, and the users are sometimes just simple phones. So how can you train or use federated learning for large models? For example, large DNNs, resonant models, transformer models, etc. So the key question is how to train large DNNs over resource-constrained devices. The way that we have been looking at this problem is through formulating it as a knowledge transfer. meaning that in the basic federated learning, you train locally and then you aggregate the models. But here you cannot train it locally. Instead, we want to view this as a knowledge transfer from light clients to a big server. And this way you can afford to maybe run smaller models and train a bigger model collectively with the help of the server. So this is based on a work that we presented a couple of months ago at NeurIP's conference called Federated Group Knowledge Transfer. And the idea, as I mentioned, is that you want to have a compact, a small model at the users, and then leverage the knowledge transfer from the user to train a big server-side model. And the question is how to define this optimization problem, because both the edge nodes should help the server and the server should also help the edge nodes so they can extract the knowledge. So it's kind of in two-way optimization problem that should be formulated. So let's see, how can we define it as an optimization problem? A naive way, like a first formulation would be to have a simple, model, which is a feature extractor followed by a classifier at each node. And then this messy equation, what it would mean is that each user locally tries to come up with a model that minimizes the loss locally at that user. Now, once they do, they're gonna send their features, like hidden features, to the server. The server has the hidden features and the labels of the users. Then it would train a bigger model based on, like these hidden features, you can view it as the knowledge that is extracted by the edge nodes to train a bigger model. The advantage here is that we are doing lightweight models at the clients, and we are training a large and effective model at the server, and requires a small communication because typically these hidden features are going to be much smaller size than the model or than the dataset. But the problem is, since the amount of data at each user is limited, at the end of the day, the features, the hidden features they generate is going to be poor quality, meaning that they are generating poor quality features and providing it to the server. And that would mean is that the server would also cannot improve the performance of its big classifier, big model beyond the threshold because it's getting like crappy inputs. So somehow we want to close the loop back so the server can also help the users to come up with better feature extractors. And one way to do it is to add a knowledge distillation loss between the logits or the soft labels that are predicted by the server and what is predicted by the client. What it would mean is that once the server comes up with a classifier, it provides its soft labels to the clients. Now the clients not only try to minimize their own loss, they try to make their prediction closer to the bigger server prediction. So in a way, they improve their own performance. And then in the next round, they're gonna help the server to improve the performance. So this goes iterations. And this way, what would happen is across different iterations, as the time progresses, the users bring their predictions closer to the server. The users absorb the knowledge of the server, and the server also absorbs the knowledge of the users. So they collectively improve their performance. That's the idea of our scheme, federated group knowledge transfer. Now let's see, how does it perform? What is the promise of this scheme? What we have done, we have run extensive experiments. And here I'm showing you an example of it. So let's say we look at first the scenario that we are assuming that all the users can train a big ResNet 56 model. In reality, that could be very cumbersome to do, but that's, let's say for now, they can do it. So that would be like assuming all the users are powerful to train a large model. In our scheme, FedGKT, we bring the user-side model to a very tiny ResNet 8, which is just a convolution followed by, other layers. Okay, so you apply a much smaller model at the users, then you apply the group knowledge transfer to transfer their knowledge to train a large ResNet 56 at the server. The question is, could we match the performance assuming that you are training ResNet 56 everywhere? So we have looked at this training for a variety of data sets, C410, C400, and much more challenging CNIC 10. The blue plot is the left side, like the best you can hope for. The red plot that I show you is for FedGKT. These plots are the accuracy of the test accuracy. As you can see, the group knowledge transfer is matching the performance of best training the large model everywhere. So in all the data sets is matching. Sometimes it's even getting a little bit better because it's a smaller model, so the generalization performance might be better. So it's matching the performance, but it requires, if you compare the amount of compute that is needed for ResNet 8 at the user compared to ResNet 56, about 10x improvement in the number of flops that is needed. If you look at the number of, like the memory size, the number of parameters, it is going to be more than 50x saving on number of parameters. And in terms of the clock time, about 15x saving. Okay, so as you can see, these methods show that the way of viewing federated learning as aggregating the model is just one way. And much more powerful ways are perhaps viewing it as, transfer learning or knowledge transfer. And those methods are just, this is one of the earlier works, one of the first works that look at federated learning for large models, but there are many exciting problems in this domain. For example, one question that we don't know the answer is how small can you make the user's models? Are there like maybe information theoretic limits that if you make it smaller and smaller, at some point, this system is going to collapse? Another part is these schemes require exchanging hidden features. But how would you provide or prove privacy guarantees of passing the hidden features? Another advantage is, in FedGKT allows different models at the user, so it can provide model adaptation and personalization by picking the models. So there are also works on maybe, coming up federated neural architecture search to use model adaptation to provide the personalization at the users. So here is an early work that we have done in that domain that if you're interested, you can take a look. All right, so that was for the second part, showing that how to formulate federated learning as knowledge transfer to address the issue of resource constraint the users. In the last part, I want to tell you about, an open source library and benchmark that we have been developing for federated learning called fedml. In case you are interested to do research in this domain, fedml is a library that all the schemes that I talked about are already available, and you can, play in that ecosystem. So here is the website for fedml library. It's also on GitHub. And maybe let me tell you a little bit overview of why we created this library. So first of all, there are currently a variety of libraries. For example, there is the Google's TensorFlow federated learning, there is Leaf, there is PySwift, there is Fate. These libraries are all excellent, but still there are many challenges that we were seeing at that time, and that's what brought us to create a new research library. Okay, so some of those challenges is the issue of data sets. For example, you want a library that all the data sets you want are available. They have a different type of models to play with, and also keeping up with the state-of-the-art algorithms. Like, for example, if you want to check the FedGKT, FedNAS, Turbo Aggregate, You want a library that they are available, and they also provide platform support for various scenarios, like whether you want to run it over IoT, mobile systems, distributed computing systems, that's what you want to have. And our goal has been to create a research library that gives you the platform diversity, keeps up with advances in research community, and supports diverse benchmarks and tasks. And that has been our motivation for creating fedml. And interestingly, many people have found it useful. For example, there are more than 350 users on contributing to fedml ecosystem, so it's growing. And as I mentioned, you are welcome to use that. It's all open source. And if you want to contribute, use it for your research, you may find it useful.
Is this based on like PyTorch, or is it like built from scratch, like from Python?
Very good. So this is based on Python, but we are actually in discussions with PyTorch to bring it in the PyTorch ecosystem too. That discussion is still going on.
Mm-hmm.
But is very easy to use. Actually, that's another advantage. Means that these libraries that I mentioned, there is a barrier for learning it. What we have seen is for people is very easy. You just download it and start using it.
Okay, great.
And also, let me highlight some of the libraries that we have recently released in the past couple of weeks. So one of those is a fedNLP. This is like a federated learning library for natural language processing. Okay, so that's the paper we released, a couple of weeks ago. As you can see, it has a lot of diverse, complicated natural language processing tasks like text classification, span extraction, sequence tagging, language modeling, etc. And for all of those, there is a lot of benchmark data sets. So what it would mean is that if you want to work on algorithmic aspects of coming up with a new federated learning algorithm for natural language processing, all of these benchmarks and the tasks are available. And the only thing you would need to do is just change the algorithm and run it. As simple as that. Another library is that we have released is for federated graph neural networks. As you know, beyond DNNs and transformer model, the graph neural networks are also gaining a lot of attention. The reason is, they capture, they are suitable for the scenarios where the data is modeled as a graph. For example, in drug discovery applications, recommendation systems, these are better models that you may want to use. And FedGraphNN, similar to the fedNLP, captures various benchmarks and data sets for graph neural network training over a federated environment. And one particular important of creating the benchmark data sets is you want to create natural heterogeneity in the data set to resemble the federated environment. And that's something that we have been investing a lot to create realistic scenarios. All right, so these are some of the libraries that we have. A third one is for computer vision. That's the library of FedCV. That, the type of problems, tasks that you would have is image classification, image segmentation, object detection. Maybe one interesting scenario for computer vision tasks where federated learning is becoming interesting is, for example, maybe across various hospitals for collaborating on oncology, like radiation oncology or imaging data, medical imaging. That's where, for each cancer type, there is very limited data at each hospital, and there is incentive for hospitals to collaborate for training better models, but at the same time, you don't want to reveal patients' data. And that's, if you are interested in those application domains, FedCV would be a right library to look at. All right, so we come to the end of my talk. I told you a little bit about federated learning and some of the works on trustworthiness, scalability, as well as the open source library and platform design for federated learning. But as I mentioned to you earlier, This area is growing rapidly. There are many open research problems and exciting, questions to look at. So if you are looking for new problems or new areas, that may be, one interesting direction to look at. Let me stop here and take any other questions you may have.
Okay, thanks a lot for your great talk. I think we have time for several questions. So the audience can make a question either in Korean or on the chat board so that I can translate into English. So are there any other questions? While we are waiting, let me ask you, actually, I had a couple of questions, but let me ask you maybe one of them. It's well known that especially in model quantization like approach of deep learning networks, it's actually sometimes this quantization as viewed, if it's viewed as like a noise, sometimes it's actually helpful to increase the performance in terms of, what you mentioned is generalization. And you used the masking at the first part of the talk. I wonder whether you can just take advantage of that noise in terms of like a generalization.
Very good. So maybe two parts. It is true. That's why, sometimes the quantized models, like doing the quantization in the aggregation would be helpful. Just something to note is that those masks that was used in the aggregation, the goal was all of them would cancel out, right?
Mm-hmm.
And those noises are typically like the same size and the same dimension as the model to completely hide the model.
Mm-hmm.
Okay. So what you're saying is maybe don't cancel all of them. Maybe that provides improvement. That can be. I don't know, but is typically, if you just add a random noise to it, I don't think that would be beneficial to do. Something would be if you do quantization, that's what I was referring at each user, and then doing aggregation, that would be better for both reducing the communication, maybe improving the performance. The challenge of it is if different users are doing different quantizations, how would you aggregate them in a secure manner?
Right.
And that's the part that becomes a challenging problem.
Right. So I think a challenge and kind of a partially open questions.
Right.
Are there any questions you can ask in Korean or English, or you can turn on your mic and ask the speaker directly? Are there any questions?
I see some questions over the chat.
Yeah.
I can read that.
Yeah. Could you answer that?
Yes. So, somebody has asked, Hong Sim has asked a question about FedGKT. The first one is on the communication overhead. So let me go back to that part of the talk. So the question is, what is the communication overhead of FedGKT, especially given that you have to send the hidden features? The other part is any comment on another category, split learning. So this is an excellent question because split learning is the one that is related to FedGKT. So let me go back. Very good question. So first of all, if you look at our paper, you see the table that we have reported the communication constraint on FedGKT. So you can look at there for the actual number. But in terms of the ballpark, you have to send these hidden features. So the size of this grows linearly with the data set. That is true. But the size of the hidden feature is much smaller than the model size. Okay, so that's where, in the one hand, you are seeing benefit because instead of federated averaging that I mentioned at the beginning, that you have to send the trained model, this would be much a smaller size. but the model size is independent of the data set, while this hidden feature grows linearly with the data set. So there is this trade-off, depends on your setting. If you are looking at a federated learning scenario where at each client, the amount of data is limited, then this would be much more beneficial in terms of even the communication. The other question was with comparison with a split learning. Just so that everybody knows, the idea of a split learning is that if you have different layers that you want to train, okay, so for example, the first 3 layers, you keep it at the client, and then you continue the other layers at the server. Okay, so now the challenge with the split learning is that you have to do forward and backward from edge to server and backward. What it would mean is that at each round, you need to have communication between edge and the server. There is nothing that can locally be done at the edge. While here, remember, the edge is locally training, and then after several rounds of local training, they aggregate and you do the training here. So meaning that the frequency of communication in a split learning is higher. That's the price that you would be paying. Again, in the paper, we have done comparison with the split learning, meaning that we have implemented a split learning in the same setting, and compared to a split learning, you will get, as far as I recall, more than 2x speed up. But please refer to the paper for looking at the exact comparison. But essentially, that would be another competitive algorithm to take a look. But FedGKT improves over that.
Okay, great. I think we are running late. Are there any other questions? Let me see, there's a...
Yeah, there is one question about how did we do the partitioning of the data to create non-IID?
Okay.
So the standard method is, applying a distribution called Dirichlet distribution. Okay, so the idea of Dirichlet distribution is, imagine each category of the data, for example, different classes, to being different bins, and a user is going for shopping to decide what data to put locally at the, at the client, right? You want to make sure this shopping algorithm is heterogeneous, is non-IID. And Dirichlet distribution gives you that. So for example, a uniform shopping is you randomly pick a category and pick a data set from that category. This would be uniform because I will do the same shopping being that the data allocation to each client. But in Dirichlet distribution, it's kind of you pick the bins with different distribution at the nodes, and then you will pick different number of the data sets. And that's what we have been using in fedml library for creating these non-IID data sets. So let me type it here. This is based on Dirichlet distribution. A better one would be coming up with data sets that have like natural heterogeneity in them. And for some scenarios, for example, there is a Google landmark data set. This is across several clients that they have taken pictures of different landmark views. There is also in NLP, we have looked at scenarios where there is a trace of the user. Okay, so sometimes you may get lucky and such an embedding would exist. And there it would give you a natural heterogeneous distribution. But most of the time you have to create it yourself.
Okay. We have time maybe for one more question before we finish. Okay. Okay. In that case, I really like to express my deep gratitude to Salman for spending your precious evening time with us. I really thank you for your great presentation.
My pleasure.
And I hope to meet you in person. I guess this is a COVID, pandemic. We are like in great distress, but in some way it's easier to actually connect globally because everybody is now working on this like online platform. Anyway, thanks for your great talk. This is really helpful and to the community, and I really appreciate it. And have a good evening.
Thanks much.
Okay. Thank you very much. And let's thank the speaker with a great round of applause.
Thank you.
Thank you very much. 감사합니다.